Good morning, guys. Okay, so after live class, so the topic which I actually first considered to do was from the chapter magnetic induction itself. But in between, I got to know that I left off a small topic from the previous chapter, which is magnetism and matter, regarding bar magnet. Actually, the same section I have sent you as examination questions, that is board exam questions. On long answer section there are two questions which are asked, right? But I have not discussed those section actually, so left off portion from the previous chapter I'm going to take it again. Okay, guys, and extremely sorry I asked the same question for examination. I didn't mean to, but I forgot. So some of you guys, two of you guys actually had written the exact answer for it, and the other guys confused what should be written or what shouldn't be written. Okay, so let's start with the question itself. You are asked what is the magnetic field along the axial, that is, if this is a bar magnet, right, and this is its axial point. So what is a magnetic field at this axial point is, let's say, P, due to this entire bar magnet. So most of you guys, right, most of you guys wrote a derivation of solenoid, right? See, guys, that section itself, of course, you are getting a point P same, and you derived an equation at P magnetic field or due to a solenoid. That derivation is also correct. But see, what was the question? What should be the question if this is to be answered by you guys? If the question had been prove that a solenoid acts or is just like a bar magnet. If that had been the question, then your answer should have been the derivation like this dx component, etc., integration, etc. Right? But that was not the question in the examination. You are asked if this is a bar magnet, there is a point P along the axial position. What will the magnetic field at B, say BP? That was a question, guys, right? So I'm going to derive it, and how to derive it's very easy, just like the electrostatic section which we derived for, remember, two charge electric dipole. The same ditto derivation it is for magnetism. Let's start. Okay, so just like the previous cases in the earlier chapter, we will draw a bar magnet here. Let's say this is your south and this is your north pole, not yours, north pole, south pole, north and south pole of bar magnet. And you are going to consider the magnetic field at point P. Let's say the bar magnet is having a length of 2L. So this is O, that is the center. Then this distance is L and this distance is L, just like the previous cases. Right. Now let's say from center O, the P point is at a distance X. Right, and let's this bar magnet has a pole strength of small, let's say it is small m. Let's not take capital M, let's take it as small m. That is a pole strength of the bar magnets. Each pole is having a strength of m. Now that means, see guys, so at P point, two type of magnetic field will be acting. One is due to north pole, the other is due to south pole. Due to north pole, the magnetic field lines are always away from the north pole. So due to north pole, the magnetic field I will draw like this. Let's say it is B1. Now at P, due to south pole, there will be a magnetic field. Let's say it is B2, but towards south, right? Magnetic field lines is always towards south. This is B2. So at P, there are two magnetic fields, which is B1 and B2, and they are in opposite direction. So before that, guys, what will be the distance of north pole from P? How much will be the distance? The total distance from the center to the point P is X. Right, and from center to N, let's say this north, is how much? L. So this distance will be how much? X minus L. Right. Similarly, what will be the distance of south pole from the point P? It will be from here, it is X, right? Then this much portion is L. So the entire length from here to here is X plus L or L plus X. Right? Right, so this much figure should be there in your notebook, because I'm not going to redraw it, guys. So because once I no, rub it off, it is not going to come back. Now we have to write the expression of magnetic field. Let's say B1. So what will be the expression for magnetic field B1? Right, B1 will be mu 0 by 4 pi, right? Then pole strength. I told you the pole strength, we are going to take it as M, divided by distance between the, let's say, NP square, right? NP, the square, right? NP square we have just written as how much? X minus L whole square, right? Similarly, magnetic field B2, mu 0 by 4 pi M divided by same pole strength, right? But the distance is X plus L whole square, right? This much we know, right? And the net magnetic field, see, out of this, which is bigger? See, B1 is having the denominator minus quantity, whereas B2 is having a denominator plus quantity. So as the denominator increases, the quantity decreases. So B1 is greater than B2 because B1 has the denominator least. So the net magnetic field which is acting on P will be B1 minus B2. It is not B2 minus B1. This much clear? Right. So now what we're going to do is finding net magnetic field, that is B1 minus B2. Substitute the value, guys. Mu 0 by 4 pi M divided by the initial B1 section was how much? X minus L whole square, right? Minus mu 0 by 4 pi M divided by X plus L whole square, right? Now find the difference, guys. Out of this, something is common. Mu 0 by 4 pi M is common. Inside the bracket, I can write it as X minus L whole square minus X plus L whole square, right? Now I can bring this term here and this term here, cross multiplication. That's mu 0 M by 4 pi bracket X plus L whole squared minus X minus L whole squared, and bracket here the denominator will be X minus L whole square into X plus L whole square, right? This much clear? See, this denominator, it is A plus B, right? A plus B into A minus B form. So the next step will be mu 0 M by 4 pi, right? It is X plus L whole squared minus X minus L whole squared, denominator X squared minus L squared whole square. Right, now open these two brackets, guys. Mu 0 M by 4 pi. A plus B whole squared is A square plus B square plus 2AB minus. This is again A square plus B square. So plus inside, let's say if you are having any problem, write like this. A square plus B squared minus 2AB. Right, and the denominator as it is. Right. Clear? Now what I am writing it fast, you guys can pause the video and complete it, guys. So it will be mu 0 M by 4 pi, right? In numerator section, X squared, L squared quantities cuts off, right? And there will be only 2 what? XL here and a 2XL there, right? So it becomes 4XL, right? Divided by X squared minus L squared whole square. Right, I didn't miss the step, guys. That is something which you can do, and only even a kid can do it. Right, that is equal to mu 0 M by 4 pi. Right, this one I am going to divide a little bit thing. Let's say I can write it as 2M 2L into X, right, divided by X square minus L square, right? Why did I write it? Because you know what is pole strength into distance between the poles, M into 2L, that is your magnetic moment, right? So it becomes what? I'm going to replace it as mu 0 m by 4 pi to this whole section. I'm going to write it as capital M. And what was the numerator, guys? There is an x here, and divided by x square minus L square, whole square. This is the general formula for magnetic field along the axial position of a long bar magnet. Why I am telling you long bar magnet? Because bar magnet, if you consider it is very, very large, that type. But usually, see the bar magnet, if I am considering, right, it is, say it is having a length 2L, and I am considering a point P here. Usually this distance, which we usually take it as x, is very, very greater than the length of the bar magnet. That is a condition when you say the bar magnet is small. So when bar magnet is small, in that equation I can remove the L section so that the whole equation becomes mu 0 by 4 pi 2m and the x divided by x square minus L square, right? So what happens when L square goes off and there is a square outside? It becomes x raised to 4, right? So this is x raised to 4. So out of this 1x and 1x in the denominator goes off, and you can write the equation as b is equal to mu 0 by 4 pi 2m by x cube. Right, this is the expression for magnetic field along the axial position of a bar magnet. Easy peasy. Now similarly we will do for our equatorial position also. Equatorial position, just like that of our electric dipole section. I'm sorry, you guys might be hearing some disturbances, guys. Right, so let's say take another color, black. So this is your dipole, right? Let's say this is your south, this is your north, right? I'm going to consider a point P over here. I want to find what will the magnetic field at P, right? Which is at the equatorial. I hope you understood what is equatorial plane, etc. I have taken, guys. Right, let's say this P point is at a distance d from the center of the magnet, and I hope you understand 2L is the length of the entire magnet, guys. So this from here to here it is L, to here it is L, just like the previous cases. So you are going to consider this point P. So at point P, due to south pole as well as north pole, there will be magnetic field, right? Now due to north pole, right, just like the previous case, due to north pole the magnetic field will be away. So let's say it is away like this, right? Whereas due to south pole the magnetic field will be towards, like this, right? So that, let's say this magnetic field is B2, that is just like the previous case, this is B2 and this is B1, right? And the net magnetic field B will be in this direction, right? Due to this is a vector quantity, right? Let's say this angle is theta. This is theta, this is theta. Then obviously this angle also will be theta, right? And this angle also theta, right? Clear? I think I have depicted almost all the diagram section. So what will be this distance, guys? This distance will be what? D, right? This is a root of D square plus L square. Sorry, it is not coming on. Right, it is D square plus L square, Pythagoras theorem, right? This much clear? Right, now see guys, I'm going to draw only this P point, right? And this P point we are having this B1, right? And then we are having this magnetic field B2, right? And the net magnetic field was, or I will take this direction, and this angle was theta, and this angle so theta, right? So just like any vector, I will divide this. So this becomes b1 sine theta, right? Similarly, b2, this will be b2 sine theta, whereas this section, this point gives for both b1 cos theta as well as b2 cos theta, right? Both of them are having same direction, right? The sine components, they cancel out each other and only the cos component remains, right? So the net magnetic field is the sum of cos components of the magnetic field. I hope this much is clear, right? Now let's move on, guys. So magnetic field B1 at P, due to the north pole of the magnet, I am going to write it as B1 is equal to mu 0 by 4 pi ball strength m divided by np square, right? From north pole to P, let's say it is np square, right? And we drew the figure. I hope you have drawn the figure as per the class. That is mu 0 by 4 pi m. What is np, guys? It is d squared, root of d squared plus l squared, but there is a whole square there, right? np is root d squared plus l squared. So np squared will be what? D squared plus l squared, right? And will be along np, right? I hope this much is clear. Now what is magnetic field B2? That is due to the south pole. That is again mu 0 by 4 pi m divided by pole and our point P and S squared or PS squared. Same mu 0 by 4 pi m divided by d squared plus L squared, right? It is also same value, right? Clear? And we just told that the vertical components b1 sine theta and b2 sine theta are equal and opposite, and therefore they are cancelling each other. So there is only horizontal component, which is b1 cos theta and b2 cos theta, and they are adding together, right? So the net magnetic field, which I will write, is actually b1 cos theta plus b2 cos theta, which we discussed just along, right? Now we are going to add these sections, right? What happens when we add now? So b is equal to, right? See, this b1 is, I'm going to write it again, guys, right? So this b1 and b2 are of the same magnet, right? That is south and north. So these two have the same magnetic strength. So in place of b1 and b2, I can just write it as same value, right? So I will write it as b1 itself. So there are two b1 cos theta, right? So what is b1? We just found the value in mu 0 4 pi, remember? So I can write it as 2 into mu 0 by 4 pi q divided by d square plus l square. Not q, it was m, right? Magnetic pole strength. Into, there is a factor called cos theta. From where I can get cos theta, we draw the diagram, right? This was your theta, this was our d, and this was our l, and this was root of d square plus l square. Right, so what is cos theta? It is L divided by root of d square plus L square. This is trigonometry, guys. I don't think I have to take it again. Right, so there is a cos factor. So cos theta is how much? L divided by root of d square plus L square. Right, now we have to do the calculations. So what is, this is root, I can write it as 1 by 2 also. So it becomes 2 mu 0 by 4 pi. Here itself there is 2, or I can say 2 into m into L. I can write it as pole strength if you want. I can write it as pole strength itself, right? M into 2L. So not pole strength, magnetic moment. So I will write it as m. And in denominator side, it is 1 by 2, right? Root, and there is 1 over here. 1 plus 1 by 2 is 3 by 2. So that is, I can write it here 3 by 2. Clear? So this much is same as that of the electrostatic guys. Not this much, the entire derivation is same as that of the electrostatics. So I think that's why I forgot it. Right. So what is the next step? Okay, this before going to the step, so mark this one as the general formula for magnetic field along the equatorial position of a bar magnet. Just like the previous cases, this is again for a long bar magnet, right? So what happens if that is replaced by a short bar magnet? So in short, which was we told that the distance or our d's is very greater when compared to the L, right? That is the point when compared to the magnet is at a higher distance. So what would I remove? I will remove the L factor from the previous equation, so that the last equation will be B is equal to mu 0 by 4 pi pole strength divided by R cube. Not R cube, it was what? D cube. Right. And the previous it was x is okay if you are writing x also. X. Just know that the denominator cube is the distance between the point and the bar magnet. This much clear. So you will find that B axial is twice B equatorial. This general section you can understand. Right. So B axial or magnetic field at axial is twice the equatorial. Right. So similarly guys, the magnetic axial field is always, see, remember this was your bar magnet, right? And the net biaxial is also written in m, right? Or mu 0 by 4 pi m divided by x cube, 2m by x cube, right? So this biaxial is always along the magnetic moment, right? Whereas equatorial is opposite to the magnetic moment. This is a very important section which I have discussed during the numerical. Axial is always along the magnetic moment, that is from south to north. Whereas equatorial is always, remember we have just true. I hope you understood. In axial, remember we told you the S was greater, right? When that is this distance x plus L was greater, remember? And that means the net magnetic field will be due to the north direction, that will be in this direction, right? Because S means S point is very far away from the point P, right? So the magnetic field was, remember, B1 minus B2, that means B1, that is the north pole has the higher magnetic field. So the net direction will be in the north pole's magnetic field direction. Right, so the B axial, that is magnetic field due to axial, is along the magnetic moment, because magnetic moment is from south to north in this direction, right? Whereas in the case of B equatorial, right, remember the point P was here, there was two magnetic field like this, then the net magnetic field was in this direction, right? So that means it is in the negative asset of the magnetic moment, right? So B axial along magnetic moment, B equatorial opposite to the magnetic moment. Clear? I hope this much is understood. Now we are going to find what is the magnetic field at a point which is general point other than our axial and equatorial, right? So the point is P. It is a distance r from the center of a bar magnet which is of the length 2L. Right, as you can see, I have drawn the figure earlier itself because the time can be reduced. And guys, this is not an NCERT based question or CBSE board question, but the end result is required for NEET JEE. So when you are just taught the end result, doesn't make sense. That's why I'm taking the derivation part of it. See, at point P, the magnetic field, right, let's say this M, right, this is your magnetic moment, that is from south to north, right? So I hope you have seen the angle theta which is made by the point P with respect to center O, right? So the magnetic moment, right, can be divided into two components, that is m cos theta and m sin theta, as you can see in the figure, right? So that means this point P is lying, see, this red color which I have drawn is a imaginary bar magnet which is having the magnetic moment, see, m cos theta, right? this red is an imaginary bar magnet, see, and it's having a magnetic moment, right? And that magnetic moment is m cos theta, and P is lying in the axial position of this red bar magnet, remember, as you can see, right? So that means, let's say I'm going to use now like itself, right? Say B1, right? That is a magnetic field, right, at P due to the bar magnet, which is having the magnetic moment m cos theta. So the magnetic field will be mu 0 by 4 pi in place of 2m, right? It will be 2m cos theta divided by r cube. Axial, remember, axial is 2m by r cube or x cube, right? Now this along OP in this direction, as we have seen, right? Now similarly B2, that is a magnetic field at P due to the second bar magnet, see this blue color, because that is also having a magnetic moment m sin theta in downward direction, right? So that means there is a just like an imaginary bar magnet with a magnetic moment m sin theta. But with respect to that, which one? This blue bar magnet, P point is along its equatorial. Just look at the bar magnet and the point P, nothing else. So the blue bar magnet is having point P along its equatorial. So B2 will be mu 0 by 4 pi m sin theta divided by r cube, right? It will be just mu 0 by m, sorry, mu 0 by 4 pi m by r cube in the usual case. But since the magnetic moment here is m sin theta, I have to write m sin theta here. Clear? Right. Now this B1 and B2, right, are we are consider as vectors, right? Let's say B1 is in this direction, right, along this direction, and B2 is in this direction, right, and their angle is 90 degree, right? So the net magnetic field B or B square is equal to the root goes off. If it is B, it will be root of B1 square plus B2 square, right? Clear? Now we are going to substitute the values, guys. I'm going to rub it off the figure. So B square, let's say B squared is equal to mu 0 by 4 pi 2m cos theta by r cube square plus mu 0 by 4 pi m sin theta by r cube, then there is a square above, right? So I can write it as B squared is equal to mu 0 by 4 pi m by r cube is common for both these guys, and there is a whole square, right? And here 4 cos square theta, right, 2 square. So it is 4 cos square theta, right? And from here in this term, when mu 0 by 4 pi m by r cube goes off, there is only sine squared theta, right? So there is plus sine squared theta, right? Now I'm going to write another term, that is mu 0 m by 4 pi this r cube, same, and then it's a whole square. Let's take it as, then there is 4 cos square theta. Now in place of sine square theta, I'm going to write 1 minus cos square theta, because sine square theta plus cos square theta is 1. This is B square, right? So B squared is equal to mu 0 by 4 pi m by r cube whole square. Now 1 cos square theta goes off, so there will be only 3 cos square theta plus 1, or net B. So that means it can be root, right? The entire thing will be in root. So this square goes off, so there will be mu 0 by 4 pi m by r cube, and this will be in root 3 cos square theta plus 1. So this is a general formula for magnetic field at any point, right, at a or due to a magnet. This much clear, right? So see guys, this is very easy in this case. If theta is 0 degree, or say theta is 180 degree, that means it is along axial. So this cos square theta term becomes 1. So 3 plus 1 becomes 4. So root 4 will be 2. Right. So the answer will be mu 0 by 4 pi 2m by r cube. Just substitute the values. Similarly, when theta is 90 degree, that means the equatorial position. Right. So in place of cos theta, that put 90 degree, the whole section goes off. So there will be only 1. So this term only goes for 1. So there will be only this much portion, that is mu 0 by 4 pi m by r cube. That means because due to axial position, due to equatorial position, the magnetic field is mu 0 by 4 pi m by r cube. So there is a way, if you are in examination, you are asked to derive either axial or equatorial, you can derive for a general point and you can use it as cases. Case 1, theta 180 degree, 0 degree, or theta 90 degree. Like that you can do, or you can separately by heart. Nothing is wrong, I guess. Alright, similarly again in another neat section, derivation is not needed, just a formula is required, that is a potential. Right, potential at any point due to a short bar magnet. The derivation is not at all required, guys. So it is V is equal to, there is a potential mu 0 by 4 pi m cos theta by r square. Right, this is the magnetic field, potential at any point due to a bar magnet, short bar magnet. Right, clear? So in axial, you will put cos theta is equal to 1. Right, so now axial position will be mu 0 by 4 pi m by r squared, whereas at equator, cos theta term, cos 90, the entire term goes off, right? So at equatorial position, it is 0. This is good to know things, guys. Clear?